All right, so today for geometry we're doing 8.2, which are tangents. Our objectives are to apply the properties of tangents to a circle and to classify common tangents and tangent circles. All right, so first of all, because I heard, I don't even know what that is. Well, you're not supposed to yet, okay? So a tangent is a line in the same plane as a circle, okay? It intersects the circle in exactly one point. And it's called the point of tangency. So if we look at this diagram over here, which of those lines is line DH or line MN tangent to the circle? Okay, DFG would be the, or DH, either one of those. So this line is tangent. That is a tangent line. Does anybody remember what the other line is called? MH? Mm-hmm. It starts with a C sound.
Is it this one?
Hey, you cheater.
Yeah, the secant. Good. MN is a secant, okay, where DH is a tangent. Okay, and you might want to write that over here, right? That line DH is your tangent line. Then we have a tangent segment. It's the segment of tangent that contains the point of tangency. Okay, so it contains the point of tangency. So DG. D to G. Mm-hmm. Yeah, so segment DG would be the tangent segment. All right, so if we look at our theorems then, the first one here, if a line is tangent to a circle, okay, this is the if-then statement, then it is perpendicular to the radius drawn to the point of tangency.
Oh, that makes sense.
Okay, yeah. Well, so if we look at this diagram here, if we drew a radius to the point of tangency, this is perpendicular.
So
Okay.
basically, any point on there, if you did a circle tangency line, it will be perpendicular because it's a circle, so the radius is the same everywhere around.
You got it. Okay, so the second one is the reverse of that. If a line in the plane of a circle is perpendicular to the radius at the point on the circle, then the line is tangent to the circle. So those are the converse of each other. The last one, tangent segments, okay, from an exterior point to a circle are congruent. So tangent segments from an exterior point to a circle are congruent. So if we look at this other diagram down here, okay, so we have this exterior point, okay, so tangent segments from an exterior point. So these are the tangent segments, okay, it's the segment that connects the point to the point of tangency. So these segments are congruent.
But couldn't it be not congruent? Why? If the line stops there, because can't the line stop right smack dab in the middle, and then one line would be shorter than the other?
So
like, let's say there was one line in between them. Wouldn't that still be considered a tangent line because the line stops right at the point and there's only one point?
the line stops right at the point.
Like, let's say there was a line from A down the middle in between B and D on the circle.
Then that line wouldn't be tangent.
Why?
Because it would cut through. Like if
But what if it stopped before it cut through?
No, it doesn't. That's not how it works. Because it's a line, right? It's a line in the same plane that intersects it can only intersect in one point. We couldn't extend the line. They can't stop it and say, okay, it's a tangent because we stopped the line there. That's not allowed. Because a line, the definition of a line is it continues on forever. So,
don't continue.
Right, but if they did, they would still only touch in that one point, like that point of tangency, where this one would touch here and it would go on and touch down there. It would be a secant, not a line of tangent, not a tangent line. Does that make sense?
Yeah.
Okay. So good thinking through that, though. That's awesome. All right. So we're going to apply these three theorems into example 1 here, finding the measure of each angle in quadrilateral ABCD if segment AB and segment AD are tangent segments to circle C. All right, so we've got some hints there. It says a tangent is perpendicular to a radius drawn at the point of tangency. So how does that help us?
What did that say?
A tangent. So which are my tangent segments?
The A to D and the A to B.
AD and AB are tangent. Okay, so these are the tangent segments. Okay, and so it says a tangent is perpendicular to a radius drawn to the point of tangency. CD is a segment. That's the radius. Is that what you're saying? Okay. So what's...
Perpendicular to DA?
Yep. So this would be perpendicular here. And this would be perpendicular here. Good.
I don't know why that would help us though.
Well, it does help us. Because we want to find the measure of each angle. And that's one of the angles in ABCD. Okay, so we now know the measure of angle D is what?
Equal to the measure of angle B.
Okay, it is equal to the measure of angle B. This is true, which is how many degrees? 90. Okay, those are both 90. I was just going to list them out separate. So then we just need to find the measure of angle A and the measure of angle C. And we would have solved the thing.
So how do you find those?
Would it be... Isn't it 90 squared? What you
Wait,
use to find
question.
X?
90 squared that you use to find X. What do you mean?
Isn't it 90, 30, 60?
90, 30. We don't know if it is.
Does it equal
It can be, but it doesn't always have to be. It can be any combination of those.
do the angles have to equal 360 because it's a quadrilateral?
Yes.
So then
Right? Okay, so we know,
we
just
have
a second.
to add the 90.
So a quadrilateral always equals 360 degrees. Yes, and we have a quadrilateral.
So add the 90 to get 180.
Okay, so 90 plus 90 equals 180.
Can't you do? Would it be 180 divided by 4? And
Okay.
then-
Can you write me, like this is the thing, is we like trying to get more into like writing an equation. Like you're right. What you're saying is right, but like people don't understand when you're saying like do this, do this, do this, do this as like 4 different steps, how it links together. I get it, but did you all understand anything that he just said or why?
No.
You did?
Got the 90 plus 90, but then divide by 4. Where did that come from?
Okay. Can you help? So can you help draw, connect the and this is it. Like this is why we talk about showing work and like explaining your steps. How can you link all that together?
Is it because there's 4 angles? Or...
Not because there's 4 angles.
So there's X, and that's one angle, and then there's X, or there's 3X.
Oh, yeah.
Okay, so see, we haven't talked about that yet. Okay, because this angle up here, whoops, sorry, that's my eraser, not my pen. This angle up at the top is X degrees, and this angle down here is 3X degrees. So if we know the whole quadrilateral has to be 360, we can say, okay, well that 360 has to be the 90 plus another 90 plus the 3X plus the X. That gets all 4 of our angles in there, right? And what we know about them. Awesome. So Caden was just making the connections very quickly in his head, which is the same thing as 180 plus 4x, because we combine like terms. We can subtract the 180, and so we're left with 180 equals the 4x. So now we divide by 4, And we get that x equals
45.
45 degrees. So which angle is x? Angle A. So angle A would equal 45 degrees.
45 times 3.
Okay, then we would do 45 times 3
135.
is 135. So that would be
C.
angle C. Very nice. And so here is your answer.
So question.
Mhm.
Is it a girl or a boy?
I don't know. Which one is it?
What do you mean?
Because it's pink and blue. The colors are pink and blue. So he said, is it a girl or a boy? It's a good question.
It's more of a maroon color.
All right. Okay. Good work on that one. Okay, let's look at the next one. Let's clear all this up. Okay. When a circle is inscribed, that should say is inscribed, in a polygon. Do you remember what's inscribed mean? Is it in the polygon or outside the polygon?
Inside.
Inside, okay, which is what's happening in the diagram we have. Each side of the polygon is tangent to the circle. So the polygon is said to be circumscribed about the circle because it goes outside the circle. Okay, so it says see example 2, but that's what we're getting. So each side of the polygon is tangent. It's touching in one point. Okay, each side is. All right, so we are tasked with finding the perimeter of the circumscribed, quadrilateral PQRS. And your hint here is to think about that one theorem that said tangent segments from an exterior point to a circle are congruent. So which pieces would be congruent? So like P.
S,
Oh, okay. Go ahead. You started with S.
well, PW, is it a Q?
PWQ.
And SFR, would those
S.
two be concurrent?
Nope. Okay, so let's go. Tangent segments from an exterior point to a circle are congruent. So from the tangent, just the tangent segment, from the exterior point to the circle. So if we say PS, that goes to the exterior, to the tangent, to the next exterior. That is not the point that's congruent. It's only from the exterior point to the circle. SY would be congruent to what?
PW? No.
They have to come from the same exterior point.
SZ.
To SZ. Yes. Okay, so SY and SZ are congruent. Okay, give me another set.
PZ and PW.
Very nice. Okay, so PZ and PW are congruent.
QW and QX.
QW and QX are congruent. Very nice.
And then RX and RY.
RX and RY are congruent. RX and one trace. There we go. Those are our congruent segments. Very good. Very, very good. Okay. Then how are we going to find the perimeter? Right, because now we're tasked with finding the perimeter. We add them all up. So if we said this was 3.1, then this would be 3.1. And if this is, what does that say, 2.7, then this is going to be 2.7. Okay. If you know a shortcut for that, you could do you could do 2 times each one. Yeah, there's a lot of different ways. Instead of writing 3.1 plus 3.1 plus 2.7 plus 2.7, you're going to constantly be repeating, right? So you could take each of those, the 3.1 plus the 2.7 plus, is it 1.4, okay. Plus 1.4 plus 4.2 And each of those is doubled, right? So then you could say, well, I'm going to add all that up, and then I'm just going to double the whole thing, multiply it by 2. And that will give you your perimeter. So what does that equal? Now, did you get your decimal answer? Because it's not exactly this. No.
That's what it has.
Then check it. You did something wrong. Because you times it by 2 at the end.
No.
You didn't time. You have to equals and then times 2, or put parentheses around. What was it?
22.
22.8.
I don't know how to work a calculator.
And what's my unit?
Centimeters.
Good, because it's perimeter, so it is centimeters, not centimeter squared. Very nice. Okay. See, and you guys complain about geometry, but did you notice you didn't have any proofs last chapter?
I was gone like all last chapter.
Nobody said like, hey, Miss Talbert, thanks for not giving us any
I
proofs.
did 2.
Oh, you did?
Yeah.
Okay, I swallow my words. I take them back. I'm sorry.
And I said it. You said how there's not going to be any proofs, and I said thanks. We really appreciate that.
Okay, I'm sorry then. I apologize.
You're mean.
I retract my words. I'm forgetful
Saying I'm a liar.
sometimes. No, I wasn't saying you were a liar. You corrected me. I appreciate that. I apologize. All right, so next up we have this thing called a common tangent. A common tangent. All right, and it is a line that is tangent to each of 2 coplanar circles. There's 2 different types. Okay, there's a common internal tangent. Okay, and it crosses the line segment connecting the centers of the 2 circles. So if there was a line segment between here, okay, it crosses those to be tangent. Or there's a common external tangent, okay, that does not cross the line segment connecting the centers of the 2 circles. So if we look at this diagram of our bicycle, what would you call those? The chain. Are they common internal tangents or common external? Common external. Okay, good. So in example 3, it's a little bit tougher. We want to determine the length of chain between the front and rear, not read, front and rear sprockets of a bike if the axles are 2 feet apart and the diameters of the sprockets are 10 inches and 4 inches.
Wait, question.
Mhm.
The 2 lines, are they congruent for external?
No. Mm-mm.
Why wouldn't they be? Because won't they eventually touch? And then that'd be the external point?
Intriguing. Yeah, I mean, theoretically. I don't know, because I was like, that's not what our theorems are saying. But yes, true, because they would essentially come to an external point. And then, so from here to here would be congruent. At least this point would be. I don't. And then, but they touched. They should be. I would think, yes, they should be. Theoretically. Yeah. Gotcha. I hadn't thought about that with this. All right, so it says.
So does that mean like that line and that line are both 2 feet?
It does not.
Why?
Okay. So, if the bike, let's see, if the axles are 2 feet apart, so the axles are from your center to your center.
Oh, yeah, sorry, but the 2 lines would be congruent. That's what I meant to say. For the bike.
Yes, on the outside. Yes, so we're looking from axle to axle. This one is 2 feet, but we don't know what this one and that one are. Does that make sense? So that's why this other diagram down here, that's to help us make some logical sense of this, okay, is from axle to axle is 2 feet apart. And then the radius on the one is 2 because the diameter was 4. And here the radius is 5. Its diameter was 10. And so we do not know what the x value is.
More than 2 feet.
So, and that's why it says, look at the diagram. Note that both radii are perpendicular to our common external tangent and are therefore parallel. Okay, so this radii and this radii are parallel. This line here, what's this dashed line here for?
That's showing how. Is that the height?
It is this, like, yes, and so that's like it's making, if we look down, it says segment TRZ, so from TR to Z, is parallel to CRCF, so this line down here. Okay, and it's dividing the trapezoid into a parallelogram, which is in this case a rectangle, and a right triangle. So the TR, let's see, TR, TF to Z is a right triangle.
So why would you do that, and why wouldn't you just do a trapezoid instead to find it?
That's a good question. Because yeah, it has us using the Pythagorean theorem, but I don't know. We could try the trapezoid method as well and see what we get. I'm not opposed to that. In this case, right, they've done it so we could say like, all right, well, this is the same height as over here, so this would be 2, which would make this 3. So we could apply the Pythagorean theorem. And since these are parallel, then this distance is congruent. So that's 2 feet. So let's try the Pythagorean theorem way first, and then I have no problem trying a trapezoid, like you said.
Oh, I see. The Pythagorean
Except,
theorem would be easier. So that's
yeah.
why they did it.
And if you did the trapezoid, well, the height would be 2 feet. Yeah, we could still try it and see. All right, so let's do the Pythagorean theorem.
So 2 squared plus 3 squared equals 6 squared?
You guys agree with that? 2 squared plus 3 squared?
No, it's not a common one, is it?
It's not. Okay, but again, so we're looking at this triangle here. Where is your right triangle? T sub f, okay. It's the right angle. So where is our hypotenuse? What side is opposite of that angle?
No, it'd be 2 feet.
It'd be the 2 feet. The 2 feet is our hypotenuse, right? That's our hypotenuse because it's opposite.
It's the opposite side.
The hypotenuse is always opposite of the 90-degree angle. It's the biggest angle. Now, the other thing is we have feet and inches. That's going to cause us a problem. So let's go ahead and convert this feet to what?
24 inches.
24 inches.
So 3 squared.
All right, so Lucas, put it into the Pythagorean theorem for me. Right, Pythagorean theorem says a squared plus b squared equals c squared. C is always the hypotenuse.
Would it be 2 squared plus? No, it wouldn't be 2 squared plus 5 squared. Would it?
Is
Because one side is 24, one side is 3, and one side is x.
Oh, so 24 plus 3.
24 is your hypotenuse, we already said, so it has to go on the side by itself. Right? Because our hypotenuse is the longest side, so it has to go over here.
So x squared plus 3 squared.
There you go.
is man, why can't I not? Is 24 squared like 466 or something close to that?
576.
576.
Mm-hmm.
Oh, that's fine.
Okay, then what will we do?
Then you subtract the 9, right?
Subtract the 9. So then x squared equals 567.
Then you do squared, right?
Square root. Yep.
Calculator.
Well, I gave a calculator to her too. All right, there you go.
Fruit and marbles.
23.8.
I don't want a decimal.
23.
Don't want a decimal.
24.
I don't want to, nope, I don't want a rounding. I want it as a fraction. So then like on this one, you would say second fraction to decimal and see if it gives you, nope, it's not gonna,
Square root of 7.
this one doesn't do it. 9 times the square root of 7. Yes. Okay. So,
Then when you do 9 times the square root of 7.
so 9 times the square root of 7, which is approximately what, Caden?
24.
Well, no, give me to like 2 decimal places, right?
24.81. 23.81.
23.81 inches. Okay. What did you ask me, Lucas? What did you ask?
I said when it be 9 times the square root of 7.
So yes. So 9 times the square root of 7 is the exact answer. And then we can actually get that a little further so we can know. But I wanted that exact answer first to remind you of that, right? Like if you get that weird looking number, convert it to your decimal to give me the approximate. All right, so if we looked at this, just because Caden brought that up, okay, as a parallelogram or a trapezoid, area equals B1 plus B2 divided by 2, right?
Yeah, that's the way to say it, I guess.
Okay, well, how would you have said it?
A equals 1/2 B1 plus B2.
Okay, so A equals 1/2 B1 plus B2
Don't you need H?
times the height. Yeah, so depending. That's fine. I'm good with the other way. Erase, please, erase. There we go. Okay, so how would we plug these value, like what would we plug into this one? But that's going to give us the area.
3 and 2.
Okay, time out. So this would give us the area though, right? Do we want to find the area?
No.
So is there a formula for like perimeter or anything like that that we could use? No?
No.
Okay. And we're not given the area to work backwards from, so would this be helpful? Okay. So yeah, so that's, but I'm glad we thought about it because earlier I was like, yeah, I don't know why you couldn't look at it as a trapezoid, but we know the formula for the area of a trapezoid, not anything to help us with the other. All right.
I thought I told you that I was going to lead to area, but I guess I forgot that.
Oh, maybe you did and I didn't hear you.
I probably forgot it.
Okay. All right, well then you guys can get started on your homework. It's on the front there,
Hey, you forgot one.
page 355, 1 through, oh, sorry. Right, I forgot we don't have work to do. We're just reading the definitions. Thank you. All right, what a tangent circle is. Good call. Tangent circles are coplanar circles that are tangent to the same line at the same point. Okay, so tangent to the same line at the same point. So they can be tangent in 2 ways. Internally tangent, both circles are on the same side of the common external tangent line. So circle M and circle N, these two are internally tangent because they both touch the line in one place. Externally tangent are circles that are on opposite sides of the common internal tangent line. So that would be M and P or N and P. Okay, either of those. Questions about that? Just calling them it. Okay, then you can get started on your homework.
You sure?
I think so.
Possibly.
Not 100%.